What are the most important properties of the determinant? The determinant encodes both geometric and algebraic information about the matrix. But I don't want us to feel like any one property of determinants is the most important property of determinants. I mean, how I want you to think about this is that determinants satisfy just a bunch of properties, and that what makes them interesting is the relationships between all of these different properties. Maybe the key property of determinants is this property, that the determinant of matrix A times a matrix B, A and B are both square matrices of the same size. The determinant of A times B is the determinant of A times the determinant of B. In other words, the determinant of a product is the product of the determinants. Why is this really important? Well, here's one reason why it's important. In general, matrix multiplication is not commutative. Even for square matrices, if you've got a square matrix A and a square matrix B, in general, it's not the case that A times B is B times A. And yet, look at this formula for the determinant of a product. Well, here I've got the determinant of a product of matrices. Here I've got the determinant of A times the determinant of B. The multiplication that's happening here is not in general commutative because it's the product of matrices. But this multiplication is just the product of numbers. The determinant of A is a number. The determinant of B is a number. This multiplication is just the multiplication of numbers, and that multiplication is in general commutative. But what that means is the determinant of A times the determinant of B is equal to the determinant of B times the determinant of A. And the consequence for that, then, is the determinant of AB is equal to the determinant of B times A. This is just a consequence of this formula for the determinant of a product. And the upshot here is that what the determinant is capturing algebraically is some piece of matrix multiplication which is commutative. There's even more going on algebraically. The determinant of the inverse of an invertible matrix is the multiplicative inverse of the determinant. Or in symbols, for an invertible square matrix A, the determinant of the inverse of A is 1 over the determinant of A. All right, what this is saying is that the determinant of the inverse of a matrix is the multiplicative inverse of the determinant. There's even more going on here. Well, here's the more complete story. So if I've got a square invertible matrix, then I have this relationship between the determinant of the inverse and the multiplicative inverse of the determinant. But in general, if I've just got any old square matrix, that square matrix is invertible if and only if the determinant of that matrix is non-zero. What this is saying is that the determinant being non-zero happens exactly when the matrix is invertible. And the determinant isn't affected by taking the transpose of the matrix. In symbols, the determinant of the transpose of a matrix A is just straight up equal to the determinant of the original matrix A. Well, this is already suggesting some of the excitement around determinants. I mean, putting some of these facts together, we can see that a square matrix is invertible exactly when its determinant doesn't vanish, and its determinant is equal to the determinant of its transpose. Well, therefore, a matrix is invertible exactly when its transpose is invertible. Now, I don't want you to get the impression that you need determinants to prove a fact like that. There's easier determinant-free ways of getting at a fact like A being invertible happens exactly when its transpose is invertible. But the interesting thing here is the determinant provides a framework for thinking about theorems like that. For example, if I've got an n by n identity matrix, so it's an n by n square matrix with 1s down the diagonal and 0s off the diagonal, I've got that n by n identity matrix, then the determinant of that n by n identity matrix is 1. The same is true for diagonal matrix. So suppose I've got a diagonal matrix, which I guess I'll call D for diagonal, and maybe it's got entries A1, A2, all the way down to AN down the diagonal, and everything off the diagonal is 0. Well, then what's the determinant of this matrix D? Well, it turns out to be the product of the entries down the diagonal. It's just the product of all these numbers down the diagonal, which I could write in maybe a slightly fancier way as the product, I goes from 1 to n, of A sub I, if the entries down the diagonal are called A sub I. and in fact, just upper triangular matrices. So suppose I've got some upper triangular matrix, which I'll call U for upper, and this matrix will have A sub 1, A sub 2, A sub 3, dot, 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 all the way down to A sub n down the diagonal. Below that diagonal will be zeros, and above that diagonal, I don't know. It'll be something. I don't know what's there, right? So I'm not going to say, I'm not even going to name the elements that are above the diagonal, but I've got these elements down the diagonal. Well, in that case, what is the determinant of U? It's going to turn out that the determinant of U is, again, just the product of these entries down the diagonal, which, again, I could write as the product I goes from 1 to n of A sub I for these entries down the diagonal. These are all shadows of a more general property. So suppose that A is an n by n matrix with, let's say, eigenvalues lambda 1, lambda 2, dot, 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 lambda n. Well, in that case, the determinant of A is just the product of these eigenvalues. It's lambda 1 times lambda 2 times lambda 3, dot, 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 times lambda n, which I could then write in the slightly fancier way, product I goes from 1 to n of lambda I. So this is kind of the general situation that we should think about, that if I've got a square matrix and I've got n eigenvalues called lambda 1 through lambda n, then the determinant ends up being just the product of these eigenvalues. As we move forward, we'll often see situations where eigenvalues will be explored through determinants. Now, that's not to say that you need determinants to explore eigenvalues, but I think it's neat how determinants make a lot of connections between different properties of matrices. Right? I mean, determinants are connected to the geometry. They're measuring how volume and areas are scaling, and they're also related to algebra. I mean, most simply, the fact that determinants are related to the fact that the matrix is or is not invertible. And these connections between geometry and algebra, between eigenvalues, between determinants, making those kind of connections is one of the really fun things about linear algebra.